This is just going to be a quick summary of what happens during glycolysis. You'll notice there are two different parts of this reaction. There is an uphill part, which represents energy being put in, and a downhill part, which represents energy being released. So you'll notice that there's more energy released than what we put in. But what makes glycolysis different than the other pathways is it requires the input of energy in order to get going. And a lot of times in chemistry, this is called activation energy. So you'll notice we start out with the glucose molecule. We will just be keeping track of the carbons on that glucose, nothing else. So you'll see C6 for our glucose representation. The first thing that happens is an ATP is converted to an ADP. This releases that phosphate ion which attaches itself to the glucose molecule. The next step is exactly the same. A molecule of ATP is converted into a molecule of ADP, releasing another phosphate ion which attaches itself to this molecule. Now this isn't glucose anymore because it has the two phosphates attached to it, and it's also undergone a couple other transitions, but it still has a carbon-6 backbone. Now when we get to the top, that carbon-6 splits into two separate pieces, each carbon-3, and each holding on to one of those phosphate particles. One at a time, we'll take those down the hill and regain our energy. At the first stop, another phosphate is added to this carbon-3 backbone. We stop again, and in this stop we turn an NAD plus into an NADH. That oxidizes the carbon-3 backbone and reduces the NAD plus. At the last stop, one of the phosphates is released to turn an ADP into an ATP, and the last phosphate is released to turn another ADP into an ATP. What we have left is just a bare carbon-3 backbone, which is called a pyruvate. This molecule will be used in the citric acid cycle. Next, we'll take our other C3 backbone down. On its way down, it picks up that phosphate ion from solution. Now we have a 3-carbon backbone with 2 phosphates on it. It becomes oxidized by NAD positive, turning the NAD positive into NADH. It releases one of its phosphate ions to ADP to turn it into ATP, which is high energy, and then it releases the last phosphate to turn an ADP into ATP. So ATP is much higher energy than ADP, and NADH is much higher energy than NAD+. So we're ending with more higher energy products than what we started with. So if we were to write out this reaction, as far as what sort of materials we're putting into the reaction and what materials we're getting out of the reaction, we would start with one glucose molecule. So this entire pathway represents all the needed materials for one glucose molecule. So we have one glucose molecule that we're putting into this system. We need to put in 2 ATPs. Those were the first green boxes that we started with. 2 phosphate ions we put into the process. 2 NAD pluses were put into the process. And 4 ADPs. Those were the 4 green boxes on the right-hand side before they got converted into ATPs. Now what we're getting out of it is exactly what you see on the screen. We're getting out 2 pyruvates. We're also getting out of this process 4 ATP, which are shown in the green and yellow boxes on the right-hand corner. We are also getting out 2 NADHs. And these are higher energy than the NAD pluses that we started with. And we're also getting out 2 ADP. So these are our products of our reaction. Now we're going to look at what we netted. Now I'm not going to write down everything that we net in this pathway, but I will write down the important things that we're netting. So we netted 2 pyruvates, which is something that we wanted out of this reaction. Those are the things that help go into the citric acid cycle. We also got out 2 NADHs, which will go into the electron transport system and turn into ATP. And then we got out 2 ATPs, which it might look like we got out 4 ATPs, but 2 of them were put in, so our net amount getting out was 2 ATPs.